Hello, welcome to the Preferred Utilities Basics of Flame Safeguard webinar. I want to thank each of you for taking the time to participate today. Understanding the proper operation of the flame safeguard is really essential for safe, reliable burner operation. Before we get started, allow me to introduce myself. My name is Steve Pelt. I'm Preferred's VP of Business Development. Before I came to Preferred, I spent over 20 years with FireEye. We also have David Eoff, Preferred's National Sales Manager, on today. He has been with Preferred for over 20 years and can certainly answer any questions on Preferred products that I'm not familiar with. For those of you that might be or not really familiar with Preferred Utilities Manufacturing is a family-owned business based out of Danbury, Connecticut. The company's been in business for over 100 years. Preferred's focus is on producing burners, fuel handling systems, instrumentation and controls, and nuclear power outage support equipment. We strive to use American-made components and parts, and I would encourage each of you to spend some time on our website at www.preferred-mfg.com. There you're going to find the details, specifications, and operation manuals for our products there. If you have any questions through this, please enter those on the chat side of this, and there will be opportunity at the end of the presentation also. Now, without any further delay, let's begin.
All right, thanks for that introduction, Steve. That was awesome.
So today, our objectives are basically going to be to understand the basic operation of a flame safeguard system. I can't stress the importance of understanding the controls on a burner and anything we can possibly do to advance your knowledge of these controls. We want to make sure that we answer those questions and make sure you understand. So we're going to be also talking about the basic flame safeguard terminology. So you'll understand when someone uses a particular term, what they're referring to. You're also going to understand the different types of flame detection and basic troubleshooting methods. Well, also, we want you to learn the sequence of operation of the preferred control systems and the basic system checks that occur at each step. These controls are made and designed to make sure that everything is done in a particular sequence, very safely and repeatable and very reliably.
And Steve, the scope of this webinar is single burner boilers, correct? Except for maybe flame detection, it's not going to be multiple burner boilers?
That's exactly correct. Yes, sir.
Okay.
Absolutely. Simple flame safeguard stuff. Okay. So why flame safeguard? Well, it all boils down to safety control. We want to make sure that this particular combustion process occurs in a safe situation at all times. The flame safeguards are a dedicated function piece of electronics. So it is basically can be configurable, but the basic sequence of operation is always the same. And it's defined and controlled by codes and standards. It also displays stamps of approval agencies. So when you're looking at a flame safeguard, you can tell whether or not it is a rebuilt control or it is a control that was manufactured at that particular manufacturer. And it performs fail-safe operation. If anything in the control is failing, it's made in such a way and designed in such a way to protect the equipment and make sure that everything shuts down and is locked out in a safe fashion. So the first thing, it does perform a controlled startup and shutdown and monitors the safety interlocks. That's the basic operation. Controlled operation monitors the flame signal at all times. And of course, it's made to protect lives, first and foremost, and protect the property, obviously. So what is it? Flame Safeguard, it's a dedicated controller consisting of a control, a flame scanner, and basically there can be components in that control that are replaceable. Certain brands allow that. There will be things like programmers, amplifiers, timing cards, and so forth. Other brands will have it all built into one control, like the preferred Flame Safeguard. So it's designed specifically and engineered to monitor, control, and ensure the safe startup and operation of a single boiler burner combination. That's what it's made for. Codes and standards come into play here. The manufacturers work together with approval agencies like UL, CSA, to come up with codes and standards that make sure that any manufacturers of Flame Safeguard follow the same strict standards to ensure they've got a very safe control design. UL 372, the primary safety controls for gas and oil fired appliances, is one such standard. UL 795, commercial industrial gas heating equipment, is another. UL 296 for oil burners, and NFPA 85 can come into play. Those are a few of the codes and standards. So when it comes to Flame Safeguard, there's different types, okay? When you'll hear the term primary Flame Safeguard, that's the most basic control. And it's basically designed to just start and stop a burner that may be just a single firing rate type burner, or it could be actually set up to do like a low, high-low application, non-modulating, usually below 400,000 BTU, and it's where proof of closure on the fuel valve is not required. That's where the majority of the primary Flame Safeguards will be applied. Over the years, these have been applied to larger applications, but there's usually a requirement for a proof of closure after you get above 400,000 BTU. There's also the programming Flame Safeguard. And this is a more advanced Flame Safeguard that will have a modulation circuit and usually above the 400,000 BTU level where a proof of closure circuit is required, and it will have that. And you'll also see, and has become more and more popular these days, the integrated Flame Safeguard and parallel positioning air-fuel ratio control. So it's all integrated into one package. Now, a lot of these packages will have separate microprocessors, one for the Flame Safeguard built into it and the parallel positioning, keeping those two functions separated. Some are not, most are. So you've got a programming Flame Safeguard and that air-fuel ratio control where you can go in and save those air-fuel ratio curves, which control servo motors for a gas valve and a combustion air damper. Can be an oil valve also. And you would store points to build a curve from low fire to high fire, keeping the air-fuel ratio where it needs to be at each firing rate step. This will also contain many of the control features required on hot water or steam boiler applications also. So a much more advanced control that can do quite a bit more. So when you get away from a linkage type modulation control, like the programming Flame Safeguard up above, and you go to more precise servo controlled air-fuel ratio control, that's where you'll get into the parallel positioning. So what does our flame safeguard control actually do? It sequences the operation of the burner to conform to safety codes, as we mentioned before, controls the fuel valves, and supervises the flame. It monitors the various safety limits installed on the burner. And it provides fail-safe operation checks by the internal watchdog relay. Now let's explain what this watchdog relay is. Anytime we have a processor-based control, or even if it's not processor-based, there needs to be a circuit that's totally independent that allows for a certain amount of time for the processor or the electronics to get from one monitored position to the end. So if you're thinking about a microprocessor-based control, once it goes through that program, it will set a actual relay, if you will, and then start again. If it does not get through that code in a certain period of time, something is not performing properly, and therefore the watchdog relay will actually cause a lockout and a shutdown, protecting the equipment and protecting many times the flame safeguard itself. So let's talk a little bit about the inputs required for a flame safeguard. First of all, we're going to have power. And most of the time, the flame safeguard units will require 120 volts AC. You'll also have to have an operating control input. And what that is basically the call for heat. So there will be an external pressure control device or something along those lines that will actually provide a closed contact, which is the call for heat, which initiates the start sequence of the burner through the flame safeguard. We also have to have a flame scanner signal input of some sort so that we can verify that we have flame when we called for it and make sure that we don't have flame when it's not supposed to be there. We also have inputs for safety interlocks. These are going to be interlocks such as a combustion fan pressure input. It could be a low water level input, those type of interlocks. Those have to be through the flame safeguard to make sure that we shut everything down if one of those opens and creates an unsafe condition. Safety permissives have to be there also. This would be like watching the proof of closure on the fuel valves. If we don't have proof of closure, we will not start the burner start process. So that would be an example of a safety permissive. Also, looking to see if there's flame on that flame scanner when we're in off condition. That's another safety permissive that can be always there.
So Steve, just to add to your inputs point there,
Yes,
if
sir.
you lose one of your if you lose the signal from your operating input, you don't trip the burner, you just shut down the burner because you have no load. Whether it's high steam pressure or operating steam pressure, operating hot water. And I guess sometimes the first water level shutdown can be in the operating limit as well.
That's exactly correct. Absolutely. That way, when the water is made up and we get above that first low water, it will go ahead and allow the burner to restart. And go ahead.
It freaks me out, and I'm sure I'm not the only one. Sometimes you'll come up to a boiler and it's not running, and you look at the control, and just like the display says here, start limit open. So it lost its operating limit because the boiler is either too hot or too high steam pressure, and it's just waiting for more load.
Correct. Exactly. Instead of actually displaying like a set point satisfied, you know what I mean?
Right. So
instead of just start limit open, but then again, that's kind of the terminology that everyone uses. So, and to your point also, the safety permissives, are different also. If something is not in the proper position, say you had draft control and it's not open when you have an operating control, it's not going to continue the start process until obviously a safety permissive closes, and also could be airflow control also.
Okay, thank you.
Okay, let's talk about the outputs now. When it comes to a flame safeguard, we have to have an output for the combustion fan motor. This will usually be an output that will go straight to the motor contactor. In some instances, if we were talking about a flame safeguard using a variable speed drive, then obviously that would go to that. But most of those applications on the simple flame safeguards will go to a combustion fan motor starter. We have an output for the ignition transformer. We have an output for the pilot fuel valve. We have output for the main fuel valve or valves. We have a circuit, if you will, which is usually a relay type circuit for the modulation. And we have an alarm output. This is usually a 110 volt output to turn on a light or a piezo type horn. Now, the primary safety control, it's basically an automatic control that programs the burner through a safe startup and shutdown in response to the inputs from that operating and safety limits. It provides the required timings in proper sequence for purge, trial for ignition timings, and flame failure response timing. The control operates with a flame detector, which transmits to the control the presence or absence of flame. Now, a programming control has all of those features and capability, but it also will add the proof of closure input to make sure that our fuel valves are closed before we call for them to open. The operating control. The operating control is usually an external device that will give a closed contact to the flame safeguard, based on the load demand. And there will be what we would call a call for heat and then a cut out point. And this could be steam, or this could be like water temperature even. So once we've satisfied the demand for the steam and it gets above that set point by a certain amount, depending on the device, okay, it will then go ahead and tell the flame safeguard will then start the shutdown sequence and go back to standby. Now, purge. Purge is when we will go through a time period where we turn on the combustion air fan and introduce air in the combustion chamber in such a manner that we replace that air inside the air to make sure that there is no gas present before we light off this burner. Pilot. This is usually a small burner, if you will, that will be used to light off the main flame. So we use it to ignite the fuel at the main burner or burners. Direct spark. When we see this terminology, that means that that burner does not have a pilot, and we are going to light the burner off directly with spark from the igniter. Intermittent pilot. When you hear the term intermittent pilot, it means that the pilot will automatically light each time there's a call for heat, and it will stay on the entire burner cycle until we go back to a standby condition. So it's always on anytime and right before the main burner comes on. On larger burner applications, you're going to have the interrupted pilot. This is where the pilot comes on for each start sequence, but will shut off automatically at the end of the trial for ignition period. So only the main burner will stay on, the pilot will be off after the PTFI period. Interlock. A device used to prove the physical state of a required condition and to furnish proof to the primary flame safeguard control circuit. So the start interlock, the safety interlocks have to be proven prior to start of the sequence. For instance, a fuel valve proof of closer switch. The running interlock. This is where the safeties come in and must be closed and remain closed during the entire firing period. For instance, an airflow switch. In the start sequence, when we bring on the combustion air fan for purging, that airflow switch has to close within a certain number of seconds. A lot use 10 seconds, but that has to prove airflow before it goes to the next step, which is then the purge timing. Pilot trial for ignition. PTFI is what you're going to hear as the terminology there. That's the period of time during the light off of the burner, which the flame safeguard control permits the pilot valve to be open before the flame detector is required to prove the presence of the pilot flame. Main trial for ignition. This occurs after PTFI, so after the period of time during the light off of the burner when the flame safeguard control permits the main fuel valve to be open before the flame detector is required to prove the presence of the main flame. So basically, in a interrupted pilot situation, we would bring on the igniter and the pilot. We would go through the PTFI period to ensure that we do have a pilot through the flame detector. At that point in time, we would bring on the main fuel valves and start the main trial for ignition with the main valves open, and that basically would be after we turn off the igniter and the pilot. So if it's an interrupted application, that's when we would be seeing the flame from just the main flame signal strength. This is a very important thing to understand, and it is different on different flame safeguards in the industry. They have different numbers and so forth. So this is something that you would want to go to the particular flame safeguard instruction manual and see what the range is. And that will indicate what a good flame signal is normally. Flame failure response time, also a very important term. This is the interval between if we were up and running, for instance, and all of a sudden our flame detector was not giving us a flame signal. It's the amount of time from the time it loses flame signal to when we shut all the fuel valves and go into a lockout condition. That's what the flame failure response time is. On large burners, it can be less than 1 second. And on most applications, in boiler applications, you will see it in the 3.5 to 4 second time period. So this is the larger the burner, the faster you want the flame failure response time as a rule. This is usually dictated by the flame safeguard, either in the amplifier or in the setup or configuration of the flame safeguard.
Yeah, Steve, I wanted to point out with that preferred 5004 M85 that you were showing earlier, your purge time and main trial for ignition time and flame failure response time are all set by dip switches that burn in after so many hours that the programmer is powered. Some of the other flame safeguard manufacturers have a lot of different permutations of controllers to buy for different timings, and we do them all with one. And the advantage is you only have to stock one flame safeguard module, and you only have to carry one on your truck for spares.
That's a very huge selling point, and it's really great for service people because, again, you've got one control that does it all. And that's a very good point. And I think the burn-in is also very, very important too, because if you're powered up for 4 hours straight, and I mean powered up, it will then burn in what those settings are. So it's very crucial that you make sure that if you want some more time, that you power down, then to power back up.
You definitely want your combustion technicians setting those dip switches and not somebody at the plant.
Exactly. To continue with terminology, you have a safe start check, and this basically prevents the burner from starting if a flame is sensed. Okay, and this is something that you definitely don't want to. You want to make sure that you go into a lockout condition if you have flame when you're not supposed to have flame. Now, how could that happen? This could happen from a fuel valve that's possibly leaking. This could happen from a UV tube that's in a runaway condition, and you really don't have flame, but it thinks it's telling the control it has flame. So this is a very good safe chart or safe start check that needs to occur. Air damper. This is usually the plate or valve to control the flow of the air in the combustion process. And so many of these forced draft air burner applications, that particular combustion air fan is going to run at synchronous speed. In other words, it's going to run at approximately 3,600 RPM. And basically, you use this valve to control the air into the combustion process. And that will be modulated along with the fuel valve to maintain a particular air-fuel ratio control or point. Airflow switch. This is a device that is to indicate that there is air movement in the combustion chamber, and some will call it a sail switch. This is very important to prove that you got airflow before you basically go in to your initial purge timing, and that way we ensure we don't have any fuel maintained in there when we light this burner off initially. Butterfly valve. This is usually a throttling valve which rotates the disc, okay, to vary the amount of gas flow, for instance. That's where this would be used. This would be modulated along with the air damper. Airflow ratio, that's what we're talking about. Regardless of whether it's linkage or we're using parallel positioning, we want to make sure that we get the airflow ratio as close to optimum as possible. Excess air, which a lot would consider 10 to 30%, is basically just we're spending a lot of fuel just heating air. We're not getting the most efficient flame, and that's the reason we want to keep the air-fuel ratio as close to optimum as possible. Firing rate. This is the rate which the air and fuel are supplied to the burner. So at low fire, we're going to basically be turned down as low as that burner is stable, okay, to give us the largest amount of modulation range, okay? So that firing rate could go from anywhere from, we say 10% a lot of times, to 100%. That's what we'll be referring to. Low water cutoff. This device is effectively a safety shutdown or lock out the burner when the water level falls to a predetermined low level. And as David mentioned earlier, a lot of applications where they may have an interruption of water flow for whatever reason, they will have a low water cutoff slightly above the low water cutoff, which will allow then a shutdown and a restart once the water level has been reestablished. Refractory. This is a heat-resistant material used to line the furnaces in kilns, in ovens, you name it. But basically, it's there to not only maintain a certain amount of heat, but also insulate. And it can be a challenge sometimes when it comes to sighting flame scanners. And we will talk about that a little bit more later. High limit. This is a device which continuously monitors the controlled variable, whether it's steam or hot water, and it responds immediately to an unsafe condition to shut down and or lock out the system. An example would be a steam boiler with a high limit that has to be manually reset. So if the steam pressure ever got to that point, for whatever reason, and it shouldn't, because if everything is operating properly, there would always be a limit before that would take the burner into a standby or off condition where it could restart once again when it needed steam. But if we ever hit this high limit, something else is going wrong, and that's the reason for a manual reset on this type of limit. Now, what are the causes for most burner accidents? Well, most of them happen at startup. Most of them, it's because of inadequate purge. Could be that the pilot is not adequate to actually light off the main burner properly. Could be that the main trial for ignition is too long. And one of the scariest is basically repeated attempts to light off the burner. Obviously, we have purge and post-purge to do as much as possible to get the fuel out of the combustion chamber. But when we start talking about oil burners, for instance, there have been a lot of accidents where people have continued to try to light off a burner, and you just can't possibly purge it enough. At some point in time, it has to be serviced, taken apart. So there's the most dangerous time is during startup. And during run, there can be some situations where you have a flame failure, and for some reason it reignites off the hot surfaces. This is the reason the flame failure response time of your flame safeguard is important. If that flame goes away for a few seconds, we need to make sure we go into a shutdown and lockout condition, because something has happened during a run condition that was not correct and needs to be addressed. Flame blowout, this could happen also for a variety of reasons actually, but again, with the proper flame failure response time, that will be caught, it will be locked out, and we'll let the operators know that an unusual and unsafe condition occurred. Now, rich air-fuel ratio firing. This is also extremely dangerous, particularly in the winter months when a lot of operators will tend to start closing the air inlets into a boiler room, for instance, and quite honestly, the burner will then start firing rich. And if someone then opens doors or something happens where it gets a burst of fresh air, you could actually have a mild explosion, you could have a bad explosion. So that is extremely important that the air-fuel ratio is monitored properly. And miswiring, unintentional and intentional. Way too many times over the years, we've seen where either an operator or maybe a technician that was not practicing the best solutions may have jumpered around, for instance, a airflow switch or something along those lines. That can happen. And so therefore, this is one of the reasons that over the years, flame safeguard manufacturers have continued to add safety checks to make sure that things aren't jumpered out and make sure that certain outputs do not have power on them when they're not supposed to. So anytime someone looks at a flame safeguard and feels like it's, oh, that's a fairly simple device, they have no idea how much that control is actually monitoring outputs and inputs in with a secondary controller that's actually inside there. So it has to be monitored internally. So if we're talking about flame detection being so important, what are the different types of flame detection are there? Well, obviously in residential applications like a water heater, they use thermocouples. However, that's where it stops. For flame detection, anything larger, you go away from heat or temperature. Now, the next step could be direct contact. This could be a flame rod, okay, or flame ionization. And this is used on a lot of different types of burners, makeup air type units and so forth. Not so much in boiler applications, but understanding this is important because it is one of the ways that we can detect flame on larger burners. Optical, definitely the most popular, no question, particularly on larger burners, commercial and industrial. And these will come in different flavors, UV, which is ultraviolet, and then ultraviolet self-check, which we will talk about a little bit further, and infrared. Let's talk about flame ionization or flame rectification. In the combustion process, molecules in the flame actually collide, and this creates free electrons and positive ions, okay? And this reaction actually occurs in such a way that if we have a way of taking a conductor in and putting it into the flame, we can actually then conduct current through that flame to a grounded area, okay? Now, that grounded area needs to be about 4 times the area of the flame rod that's entered into the flame. And most of these applications, the flame safeguard, it provides an AC signal to that flame rod electrode. When a flame covers the electrode, the AC signal is then conducted through the flame to ground. This ground is usually the burner face. The current through this flame is usually in that 2 to 6 microamp range. So it's a low current, but it is very reliable for the most part. If a high current is sensed, then the control recognizes it as an electrical short and not a flame. Now, everyone would say that's fantastic. This is a great way of doing it, but it's not without its issues. For instance, corrosion deposits through, from the combustion process or a cracked insulator. When that happens, you are down, no question. Now, this flame rod, if you will, it's usually made of a material such as canthanol, which is rated up to 1200 degrees C. So we can insert that straight into that flame without issues. Again, this type of flame detection is going to be used on the smaller burner applications. Very popular, like I said, maybe before on the makeup air type units. The advantages of a flame rod or flame rectification is flame discrimination. The nice thing about that rod is we can say we want this much flame out to this point, or we're not going to recognize it. So in other words, we can actually determine how far we want that flame length to be. So that is a real nice way of doing it. It is quite inexpensive for the most part, and it's very easy flame signal processing from an electronic standpoint. So there's some real advantages to it. The disadvantages, corrosion. You put it in some difficult applications around, for instance, in petrochem type applications where we have a corrosive type atmosphere. They do not do well for a length of time in those applications as a rule. The combustion deposits happen. Can they be cleaned? Yes, but does it become a reliability issue? It can be. and they can be very easily damaged. A cracked insulator on one and you've got a short and it will not operate correctly.
So Steve, just to clarify, what the corrosion does is it builds up a layer on the flame rod that the ions can't pass through, so it acts like an insulator. And I've actually found that it's more of a problem on units that don't fire as much, more so than units that fire a lot. Because when the unit's down and it's condensing, that's when it gets wet and the flame rod will corrode.
You're absolutely spot on. You are absolutely spot on. And I've always wondered, why, like for instance, in a makeup air type unit, which is on a roof of a building, you would think, oh, there's no way because they're off so much of the time. However, they're not really good on the UV side of things because they generate so much moisture. So it actually ends up being the better way of doing it in that type of application. So, but you're exactly spot on. If they're set to where they can actually corrode without getting something to basically dry it off on a regular basis, you can have issues. Exactly. Okay, optical flame detection. Well, if we're going to be looking, if you will, at a flame, we have to have a sensor that is sensitive to a particular range, spectral range that combustion process is going to actually generate. And what you would find so much of the time with gas or natural gas type flames is you see a lot of energy in the ultraviolet range. This is why the UV tubes were actually developed many, many years ago and centered around the low ultraviolet range. Around the 200 nanometer range is where they really look, and there's a lot of energy from a gas flame in that range. It's really nice because it becomes really blind to visible light, which makes it a safer flame detection device. So it really works well there. Now, when we start talking about burning oil or coal or something along those lines, there's a lot more energy in the infrared range. And this is where a lot of those devices will be centered, if you will, or most sensitive in that 1000 to 1100 nanometer range. Okay, again, being safe because it is not sensitive in the visible light range. So when it comes to optical flame detection, that's where we want devices to kind of be sensitive and not be sensitive. So when it comes to flame detection, an ultraviolet flame scanner or tube, and a lot of people will say it's a vacuum tube. It contains two plates, if you will, or conductors, and that tube is filled with an inert gas that allows current flow between the plates when it's exposed to enough UV light energy. So most of them have their sensitivity, as I mentioned before, the 190 nanometer spectrum range. And most flame safeguards will actually provide about a 300 to 600 volt AC or DC signal to that tube. Then when there's enough UV energy from a combustion process, that tube is subjected to that, it will provide a momentary conduction between the two plates. In other words, kind of a pulse, if you will, allows that voltage to jump across to the other side, the other plate. The stronger that light is, the more conduction. In other words, the more pulses, the more times it will conduct between those two. This is where the flame safeguard then is going to be looking, and it says, I've got no pulsing. I have basically steady state signal, which is the supply signal voltage, so there's no flame. Then when we have flame, it sees the pulsing, which is drawing that value, if you will, down. So that's when it knows that it's got a true flame signal. Now, why do we have ultraviolet self-check? Well, The vacuum tube is an extremely sensitive and reliable device for the most part, but if it's subjected to super high ultraviolet radiation for long lengths of time, we can actually get a condition which is called tube runaway, where basically that flame could go away and that tube could continue to conduct like it's seeing UV light. That is an unsafe condition, obviously. So what is recommended by the flame safeguard manufacturers is basically, if your combustion process, that burner, is going to be running for long lengths of time, usually over 8 hours at a time, that you go to a self-check type scanner, or you cycle the process completely off and back on to make sure that it doesn't see a false flame. So how are these normally done as far as self-check? Is there's a mechanical shutter built into the UV self-check scanner that will actually block off the light, if you will, or the UV radiation coming from the flame for a brief period. And the control looks for that drop-off, complete drop-off of signal. And it needs to see that continuously. The flame safeguard knows that it has to see that. Now, some manufacturers do it every 3 or 4 seconds. Some will do it every 10 seconds, but it is checked continuously, and that determines and allows the flame safeguard to determine that it is not a runaway tube and it's a safe flame detector operation.
Steve, I just want to emphasize how dangerous a runaway scanner is. If a UV scanner fails in a runaway condition, it means it's telling the flame safeguard that we have flame proven. And it's the only device on a boiler that tells you that flame is proven. So if your flame blows out for whatever reason and your UV tube is in a runaway condition, the gas valves or the oil valves don't shut off. And you just keep putting more fuel into this boiler that doesn't have a flame in it anymore. So it's very, very dangerous. And that's why the flame safeguard people like Preferred go to such lengths to prevent a runaway scanner.
Absolutely. And there's so many applications out there that have the standard UV scanners on them that really need the self-check scanners on those. So anyone that runs across an application like that and sees non-self-check, the question for the operators would be, how often do you cycle this burner off and on? And if they say it's running for 24 hours, 36 hours, days on end, that's a dangerous situation and they need to be aware of it.
Right, because it's that off cycle where the flame safeguard can detect a runaway scanner. It turns the burner off and it's looking for the scanner signal to go to 0. And if it doesn't, the flame safeguard will go into lockout and not light off again.
Exactly. That's where it will indicate the false flame. And that right there is the troubleshooting that you would know immediately. Well, we got a false flame. When did this occur? And that will tell you probably had a runaway tube. Okay. Well, what are the advantages of the UV tube, actually? Why would we still be using that technology after all these years? Well, it's very sensitive to that deep UV spectral area, which is really perfect for determining it's a true flame that it's seeing, okay? The other thing is it's quite inexpensive compared to other UV sensor technologies. There are other UV sensor technologies out there, and they are used in very expensive flame scanner applications, but the amount of signal processing required to use those type of sensors is just way beyond what you can do with a UV tube. So the UV tube is still relevant. It still works extremely well. As we mentioned, you need to use self-check where it's necessary. But other than that, it's just still a really good, reliable way of sensing combustion, true combustion. The signal created from that reaction in the tube itself is also very easily processed and analyzed. So it's something that's a technology that quite honestly hasn't changed dramatically in decades, but it's still extremely viable. The disadvantages, that vacuum tube can become saturated, as we said before, if it's subjected to enough UV radiation for a long period of time. But the other disadvantage, vibration or shock, because it is a tube and because it has leads that are going from outside the glass to inside the glass. If there's enough vibration over time, depending on the construction, it can create a leak in the tube. If that happens, we end up with many times a runaway tube. So there's another condition where a false flame could actually be indicated. Okay, infrared. This flame scanner will typically use a lead sulfide detector. The lead sulfide detector was first used in a friendly type application way back in the early 30s. And what it does is it's a particular type of cell that utilizing the lead sulfide, and when it's subjected to a certain amount of infrared radiation, the resistance of this cell actually changes. So that became a very reliable and fairly inexpensive way to consistently make a cell that could be interfaced with the controls and make it sensitive in that 1000 to 1100 nanometer spectral range. And it's something that's also that has so many years of operation out there, very, very reliable. The only thing is it does have certain disadvantages. The advantages, though, are it's very fast response. It can be quite inexpensive, and there are different sizes. So depending on the type of application, you can get larger ones for applications that need more sensitivity. It's very easy flame signal processing because we're actually putting a DC voltage on that cell, and then we're looking for that change in resistance is what we're looking for. And that is very easy to process. And you can do really good flame discrimination on it, but it usually requires a bit more signal processing, okay? And what I mean by that is, for many, many years in the industry, infrared was kind of looked at as it sees refractory, that scares us. Well, as electronics have gotten better and more complicated, if you will, most of the flame safeguards can recognize the difference between the actual combustion or burner infrared radiation versus the refractory radiation. And that was the biggest scare for that type of sensing technology for a long time, because refractory tends to generate an infrared signal that is very slow modulating, whereas a burner infrared signal will be faster modulating. Therefore, we can discriminate between one versus the other. The disadvantages.
Steve, it's very rare for an IR scanner to fail showing flame, correct?
That's exactly correct. In fact, in the industry, it's kind of referred to as dynamic self-check, because if for some reason that signal becomes steady, the controls will lock out because they're not seeing that modulation of that in other words, amplitude modulation of that ray that it wants to see. So it will see that fast change of resistance if it's true modulation. If it's just a straight line of resistance, something has shorted, something's gone wrong, but it's extremely rare for it to do that. In fact, the only applications I've seen where they have failed is they fail in an open condition. There's no resistance, and the control will lock out.
Correct. I've seen that. We refer to that as saturation, and it can be hard to diagnose because it's happened to me a couple of times when I'm firing oil and I have a great oil flame and I have a great flame signal, and then I trip on flame failure. When my flame signal was 100 out of 100, just right before, and it's because the scanner saw so much IR radiation that it lost that flicker that it's looking for and shut down. It showed no flame.
Right, right. Well, and when you're talking about optical scanners overall, okay, when it really comes into play here is, for instance, the flame scanner can only operate as well as the sighting. And so much of the time, the sighting of the flame scanner comes into play. So it's very important. And sometimes you're locked into just a sight tube on the burner. But if that has been bent or wasn't installed properly and you're not seeing full port flame, that will not give you consistent good flame detection. On UV, moisture, if you get moisture in the process, that can really absorb a lot of the UV radiation. That's where a lot of times someone will change to an infrared scanner. There's also temperature ratings that come into play too, okay? But most UV, most infrared stuff is rated to 200 degrees F anymore. However, vibrations can still be a problem. Saturation can be a problem. But those are your main disadvantages on optical. Now, let's talk about a sequence of operation. We've got flame detection now. How is this actually going to operate in starting this burner? We're sitting there in a standby condition. The control's looking for false flame and see if there's anything that comes up when it's not supposed to be. If it sees flame or indicates flame when it's not supposed to be, it will lock out, giving the false flame indication, okay? A lot of the flame safeguards also would monitor the proof of closures also during that period of time. Some do not. Some of the older ones do not monitor or look at the proof of closure valve until there's a call for heat, okay? Now, when we get a call from heat from the operating control, usually a separate device, then the safe start checks basically occur to make sure that there's not voltage where it's not supposed to be. The limits we look at, and we basically want to wait to make sure that they close when they're supposed to. And this is actually after we do a start the combustion process. In other words, combustion fan comes on. So we have to see proof of airflow within a certain number of seconds. And that changes depending on the flame safeguard, but usually it's about 60 seconds that all those limits have to be made, okay? The proof of valve closure has to be there. So we know that that valve is closed, okay? Then we've got to go into a purge condition. We've proved that we've got airflow. We know that we don't have flame because we're not supposed to. All our limits are closed. So now we're going to basically, the flame safeguard will, in a modulating condition, take the mod circuit and drive the mod motor, if it's a linkage control, to the high fire or purge position. At that point in time, this is when the purge timer will be initiated. And depending on what purge time we have calculated is required for that vessel, it will start counting down. Once that purge has been completed, then the flame safeguard will then close the low fire position and verify that it gets there before it starts ignition. Once it's got into the low fire position, some will require another timer that waits a certain number of seconds. Some will go immediately into our pilot trial for ignition time, which is basically start the igniter or ignition transformer, power to it, power to the pilot, and we go into PTFI. If we have early spark termination, then basically we will shut off the igniter before we shut off the pilot. Let me explain early spark termination and why it's needed. In certain burners, the pilot is set up in such a way and the sighting of the flame scanner that it can actually see the spark that's on the igniter on the pilot. Unfortunately, those sparks generate a lot of UV, and that can be recognized as a flame. So that's the reason for early spark termination. Is usually how the scanner is sighted where the spark is on the pilot.
And there are instances when the burner is designed right so that the scanner can't see its own spark, but if there's stainless steel inside the furnace, it can bounce the UV all around and back to the flame scanner.
And that can happen also, absolutely. Another reason to do early spark termination, and a nice thing to have as a selection on a flame safeguard. Some flame safeguards require you to change the programmer, and obviously in ours that's a selection. Okay, and then we have a selectable main trial for ignition. So we've got the pilot, we brought on the spark, we brought on the pilot fuel, we acknowledge that we've got the pilot through the flame scanner. After the PTFI time expires, we bring on the main fuel valves, and we are then in main fuel or the MTFI time. If it's an interrupted pilot, that pilot will be turned off, and we will then go through that PTF or MTFI time. And after that expires, we will go into what's called auto. And that auto mode is when the flame safeguard releases control of the mod motor, if it's a linkage type control, to an external modulation device. And then it will modulate up and down the firing rate range to maintain the set point. Now, if we're doing an installation or some troubleshooting and we want to actually stop this sequence of operation and look at the pilot or adjust the pilot, flame safeguards will have a pilot test mode, and you can turn that switch over so that it stops in the PTFI period so that the pilot can be adjusted. So we've been up and running, we've been modulating fine, and guess what? We've gone to low fire, and let's say in a steam application or hot water application, the temperature or the steam pressure continues to climb, and we get to a cut out selected point. At that point in time, the call for heat will be removed. The flame safeguard will then go into, if it's set for, it will go to a post-purge, which is usually about 15 seconds. So all fuel valves are shut off, and the combustion air is, we go to a wide open position, and we do a post-purge for usually 15 seconds. After that is done, then the combustion air fan will be shut off and everything returns back to standby condition. Pretty simple process, but a lot of monitoring is required and a lot of safety checks are occurring continuously. Now, troubleshooting. What's the number one problem usually? It's wiring. There's no doubt about it, regardless. And you will hear from many people, oh, it's been running fine for years. Well, that's fine. But intermittent shorts, something's come loose due to vibration, someone's changed something. We don't know, but it is wiring so much of the time. Now, if you get out there and certain things are not operating, period, there could be blown fuses. So once again, when it comes to troubleshooting, the simple things are the things to start with. The wiring, blown fuses. Is it starting? Do we see the pilot? What's the flame signal strength? What's the flame signal strength at pilot? What's the flame signal strength on main fuel valve? Is this where it was when it was actually originally commissioned? We could have an issue where it's simply just dirt or debris on the flame scanner that needs to be cleaned. Or we could have a flame scanner that has gotten weak over time. So that flame signal strength measurement is very crucial. Gas pressures, has something changed there? That could cause issues with the light off, could cause issues with making rate. So gas pressures need to be looked at. Power issues, no question. One of the biggest things over the years that I've seen is what's your voltage from neutral to ground? If you've got a floating neutral there, electronics do not like that. So we need to make sure that we don't have a floating neutral, because that can happen right when you're first commissioning something, or it can happen down the road. Noise, this can be EMI or RFI. So either electromechanical interference, or it could be radio frequency interference. And this type of noise can cause the controls, because they are microprocessor based, so many of them, to try to save themselves. And when I say save themselves, shut down in a safe situation. So there can be noise. So how do we prevent a lot of noise issues? Grounds. I can't stress enough. Proper grounding on everything that's required by the manuals on all the flame safeguards need to be done exactly like they're called for in the manuals. I check grounds immediately when there's any kind of issues, whether they're intermittent or consistent. Also, temperature. All the electronics have a operating temperature range. And so many times over the years, I've gone to locations where they have had issues and find out that it happens during a certain time of the day. And guess what? It could be temperature. I've actually measured temperatures on flame safeguards that was way above their operating temperature range, and they were still operating. But let them know that it was shortening the life of the electronics, and they are headed for problems. Also, contact corrosion. There's no doubt about it that, anytime you have connectors or terminal blocks, corrosion can occur. And when we're talking about certain things like a flame scanner, for instance, a slight amount of corrosion there can weaken a signal. And that's something definitely that you need to be aware of. Clean contacts, reseat, wires and so forth that are going to terminal blocks. A lot of this stuff is very, very simple stuff that can actually cure problems. Bouncing running interlocks, absolutely. Airflow switches can be problematic. Let's just put it that way. And if you get a bouncing interlock on something like that, guess what? It's going to go into a shutdown and possibly restart. And over the years, I've had many, many calls where it just shut down for no reason and restarted. Well, there was a reason, definitely. So looking for a bouncing running interlock is very, very important. This is where a first out annunciator combined with a flame safeguard can be a very valuable piece of electronics. The call for heat device can have issues. There's no question. There can be wiring on it, or it could be having some contact issues too. So basic troubleshooting, that's what we're talking about here. Wiring, keep with the simple stuff. Wiring, corrosion, contacts, those are the things to look for. And now we're open for questions.
We got a couple of questions on the email, but before we do that, I just wanted to point out that we have a couple of other Flame Safeguard webinars, previous webinars that are now on our YouTube page. So if you go to YouTube and search on preferred utilities, you'll come to kind of our home page and then click on videos, and all of our videos are there. I know we did one several months ago about the most common boiler explosions and how flame safeguard and boiler instrumentation is designed to prevent them. It probably had a better title than that, but that's basically what it did and would complement this one pretty well. First question we got is, Steve, is there a boiler horsepower range where you recommend a self-checking UV scanner versus a non-self-checking scanner?
You know, it tends to fall into the larger sizes above the 400,000 BTU. But again, if you think about it, there can be a runaway scanner even on something small. So it really goes back to if the equipment, the burner, is cycled on or off, period. Because that technology is there, and it's very clear to everyone that if that isn't cycling on a regular basis, every 8 hours, I would say, the longest length of time, it needs to have a UV self-check. A lot of companies won't do that because they cycle their equipment. But the truth of the matter is, even a smaller application could certainly dump a lot of fuel in an area and cause a real bad condition.
Okay, so it's really not related to the burner size, but how the burner is used. And if it doesn't cycle off every once in a while, then use a self-checking scanner to catch a runaway scanner.
That's exactly correct. When it comes to UV, absolutely.
Okay, cool. You know, when you really think about it, a flame safeguard system is just, I mean, they're required by code now, but really what they are is a way of automating your boiler, because boilers probably ran for 50, 80 years before they invented flame safeguard systems, but everything was just done manually. You know, you had a person watching the steam pressure, watching the water level, watching the flame, and taking corrective action or shutting down in the case of an emergency. So a flame safeguard is really an automation thing.
Yeah. We
Okay.
also had a question here. Would O2 trim catch an over-rich condition that you were discussing from someone limiting the air into the boiler room? Would O2 catch that? That's a great question because yes, that's most of your parallel positioning or any air-fuel ratio type control devices that will incorporate O2 trim will allow you to put in max and min values and either alarm or shut down. And so it's a very good, it becomes more than just a device that keeps you right on your air fuel ratio curve, if you will, regardless of the ambient conditions, but it also would prevent a super rich condition also. So it can be a safety device from that standpoint. Good question.
Preferred's representative Mario Franciscini in Puerto Rico really drove that point home to me, where, you know, it's always a beautiful 85 degrees in the afternoon in Puerto Rico, but they still use a lot of O2 trim because, like you said, it's a safety device and they burn a lot of oil. So O2 trim can keep you from smoking, you know, more so than a system that doesn't have O2 trim.
Exactly.
Okay, what are the advantages of systems that combine flame safeguard and fuel air ratio control, and are there any drawbacks?
Well, the advantages of having it all in one is basically it goes back to the size of the real estate in the cabinet. It's also one component that you're troubleshooting instead of trying to determine which component could be causing the actual issue. So when it's all combined into one unit, obviously the device is checking everything. So it really becomes easier to troubleshoot a lot of the time. So that's really there. And as far as drawbacks are concerned, there's really not that many, other than if you do have to replace the device, you are replacing the whole thing. That's basically it.
One thing I like as a previous and sometimes burner service technician is that the parallel positioning systems or the linkageless systems are a lot more tamper resistant than linkage systems. You know, it's very easy to tamper with a linkage system because they're mechanical, whereas the linkageless systems are more difficult to tamper with.
We had another question here about when would we recommend a first out enunciator? Quite honestly, anytime you have a pretty long string of running interlocks, the more there are in that string, or multiple fuels, if you will, that's where it really becomes valuable, because it's so much quicker to actually troubleshoot if you're having an intermittent shutdown or an intermittent restart. You can tell exactly which one of those switches or devices in that interlock string are actually causing the problem. Nothing more frustrating than going out there and just seeing, shutdown or seeing alarm, and then having to, basically start everything up and start monitoring. So first out annunciator can save a ton of time and basically point you right to the device that's actually causing the issues. So if it's something that can fit into a certain application's budget, if you will, they're always a good idea. Any other questions out there? Anybody got any questions?
I don't see any more in the chat, and I don't think Megan has any. So I want to thank Steve for doing this and thank everybody for attending.
Thank you all.